Welcome to our exploration of matter waves, a fascinating concept that bridges the gap between classical and quantum physics. In this video, we'll unravel the mystery behind the de Broglie relation and see how it changed our understanding of the microscopic world. The idea that particles such as electrons can exhibit wave-like properties was revolutionary. It challenged the traditional view that only light could behave as both a wave and a particle. Let's begin by setting the stage for this groundbreaking discovery and see why it matters in the world of physics. For the quantum revolution, classical physics described matter and energy as separate entities. Objects like balls or planets were considered particles, while phenomena like sound or light were waves. This clear distinction worked well for everyday experiences, but as scientists probed deeper into the atomic world, they began to notice strange behaviors that classical theories couldn't explain. This set the stage for new ideas and the eventual birth of quantum mechanics. One of the first hints that the classical view was incomplete came from experiments with light. Scientists observed that light could behave both as a wave, creating interference patterns, and as a particle delivering energy in discrete packets called photons. This duality puzzled researchers and hinted that the universe might be more complex than previously thought. The concept of wave-particle duality became a cornerstone of quantum theory. In 1924, French physicist Louis de Broglie proposed a bold idea. If light can act as both a wave and a particle, perhaps matter can too. He suggested that every particle, no matter how small, has an associated wavelength. This was a radical departure from classical thinking and opened the door to a new way of understanding the microscopic world. De Broglie's hypothesis would soon be tested and confirmed, forever changing physics. Heart of de Broglie's idea is captured in a simple equation. Lambda equals hp here. Lambda is the wavelength of the particle, h is Planck's constant, and p is the momentum of the particle. This equation, known as the de Broglie relation, tells us that the wavelength of a particle is inversely proportional to its momentum. The smaller the particle's momentum, the longer its wavelength, and vice versa. Planck's constant, symbolized as h, is a fundamental quantity in quantum mechanics. It sets the scale at which quantum effects become significant. With a value of approximately 6.626 x 10 joule-seconds, it's incredibly small, which is why wave-like behavior of matter is usually only noticeable at the atomic or subatomic scale. Planck's constant appears in many quantum equations, including the de Broglie relation. Momentum, represented by the letter p, is a measure of an object's motion. In classical physics, it's simply the product of mass and velocity. In quantum mechanics, momentum plays a crucial role in determining the wavelength of a particle, as described by the de Broglie relation. The greater the momentum, the shorter the wavelength, making wave-like properties harder to observe for larger, faster-moving objects. For everyday objects like a baseball or a car, the de Broglie wavelength is so tiny that it's impossible to detect. Their large mass and high momentum make their wave-like nature negligible. This is why we don't see cars or people behaving like waves in our daily lives. However, for tiny particles like electrons, the wavelength becomes significant and can be measured in experiments. One of the first confirmations of de Broglie's hypothesis came from electron diffraction experiments. When a beam of electrons is passed through a crystal, it creates an interference pattern just like light waves do. This was clear evidence that electrons, which were thought to be particles, also have wave-like properties. These experiments marked a turning point in our understanding of matter. Wave nature of electrons is not just a theoretical idea, it's been observed in laboratories around the world. When electrons pass through narrow slits or crystals, they produce patterns that can only be explained if they behave as waves. This discovery has had profound implications, leading to the development of technologies like electron microscopes, which rely on the wave properties of electrons to see tiny details. Double-slit experiment is a classic demonstration of wave-particle duality. When electrons are fired one at a time through two slits, they create an interference pattern on a screen just like waves. This suggests that each electron behaves as a wave, passing through both slits simultaneously and interfering with itself. The results defy classical logic and highlight the strange nature of quantum mechanics. The discovery of matter waves forced physicists to rethink the very nature of reality. It showed that particles can't be described as just points or waves, but as something more complex, a blend of both. This realization led to the development of quantum mechanics, a new framework for understanding the behavior of matter and energy at the smallest scales. With the acceptance of wave-particle duality, quantum mechanics emerged as the dominant theory for explaining atomic and subatomic phenomena. This new science introduced concepts like probability waves, uncertainty, and quantization, which have since become essential tools for physicists. The de Broglie relation is a key part of this quantum revolution. In quantum mechanics, the wave associated with a particle is not a physical wave like water, but a probability wave. This wave describes the likelihood of finding a particle at a particular place and time. The famous Schrödinger equation uses these probability waves to predict the behavior of particles, further cementing the importance of de Broglie's insight. Wave nature of matter also leads to the Heisenberg uncertainty principle, which states that you can't know both the position and momentum of a particle with perfect accuracy. The more precisely you know one, the less precisely you can know the other. This principle is a direct consequence of the wave-like behavior described by the de Broglie relation. Practical applications of matter waves are vast. One of the most important is the electron microscope, which uses the wave properties of electrons to achieve extremely high resolution. Because electrons have much shorter wavelengths than visible light, they can reveal details at the atomic scale, revolutionizing fields like biology and materials science. Quantum tunneling is another phenomenon explained by matter waves. In classical physics, a particle can't pass through a barrier if it doesn't have enough energy. but in quantum mechanics, the probability wave allows for a small chance that the particle will appear on the other side. This effect is crucial in technologies like scanning tunneling microscopes and even in nuclear fusion in stars. Wave packet is a combination of many waves with different wavelengths and frequencies. In quantum mechanics, particles are often described as wave packets, which helps explain why they can appear localized in space while still having wave-like properties. The concept of wave packets is essential for understanding how quantum particles move and interact. Inside atoms, electrons don't orbit the nucleus-like planets around the Sun. Instead, their positions are described by standing waves or orbitals, which are solutions to the Schrödinger equation. These standing waves determine the allowed energy levels of electrons and explain the structure of the periodic table. Wave nature of matter leads directly to the concept of quantized energy levels. Electrons in atoms can only occupy certain allowed energy states, corresponding to specific standing wave patterns. This explains why atoms emit or absorb light at specific wavelengths, giving rise to the unique spectra of elements. Wave-particle duality is not limited to electrons. Experiments have shown that even larger particles like atoms and molecules can display wave-like behavior under the right conditions. This demonstrates that the de Broglie relation is a universal principle, applying to all matter, though the effects become harder to observe as objects get bigger. For macroscopic objects like a tennis ball, the de Broglie wavelength is so tiny that it's effectively zero. This is why classical physics works so well for large objects. The wave nature of matter only becomes important when dealing with very small particles where quantum effects dominate. The de Broglie relation has been confirmed by countless experiments. From electron diffraction to interference patterns with atoms and molecules, the evidence is overwhelming. These experiments have solidified the wave nature of matter as a fundamental aspect of our universe. Understanding of matter waves has led to numerous technological advances. Devices like electron microscopes, quantum computers, and advanced imaging techniques all rely on the principles first described by de Broglie. As our knowledge of quantum mechanics grows, so too does our ability to harness these effects for practical use. Quantum computers use the principles of quantum mechanics, including wave-particle duality, to perform calculations far beyond the reach of classical computers. By exploiting the superposition and interference of matter waves, quantum computers promise to revolutionize fields from cryptography to drug discovery. Chemistry is deeply influenced by the wave nature of electrons. Chemical bonds, molecular shapes, and reaction rates all depend on the arrangement of electron waves in atoms and molecules. Understanding matter waves has allowed chemists to predict and control chemical reactions with unprecedented precision. Biology, too, has benefited from the discovery of matter waves. Techniques like X-ray crystallography and electron microscopy have revealed the structures of proteins, viruses, and even DNA. These insights have transformed our understanding of life at the molecular level. Materials science uses the wave properties of electrons to design and analyze new materials. By understanding how electrons move and interact as waves, scientists can create materials with unique electrical, magnetic, and optical properties, leading to innovations in electronics and nanotechnology. Even in astronomy, the principles of matter waves play a role. Quantum tunneling is essential for nuclear fusion in stars, and the behavior of particles in extreme environments like neutron stars or black holes can only be understood using quantum mechanics and the de Broglie relation. The discovery of matter waves has also influenced philosophy, challenging our notions of reality and determinism. The idea that particles can exist as both waves and particles, and that their behavior is fundamentally probabilistic, has sparked debates about the nature of existence and knowledge. Although the de Broglie relation is powerful, it has its limits. It works best for free particles in simple systems. In more complex situations like particles in strong fields or interacting with many others, more advanced quantum theories are needed. Nonetheless, the de Broglie relation remains a foundational concept in quantum mechanics. At very high speeds, close to the speed of light, relativistic effects become important. The de Broglie relation must be modified to account for the increase in mass and energy predicted by Einstein's theory of relativity. This leads to even deeper connections between quantum mechanics and relativity. When a measurement is made on a quantum system, the probability wave described by the wave function collapses to a definite outcome. This mysterious process, known as wave function collapse, is still not fully understood and remains one of the biggest puzzles in quantum mechanics. There are many interpretations of quantum mechanics, each offering a different perspective on the meaning of matter waves and probability. Some, like the Copenhagen interpretation, emphasize the role of measurement, while others, like the many worlds interpretation, suggest that all possible outcomes actually occur in parallel universes. Research into matter waves continues to push the boundaries of science. Experiments with larger and more complex particles are testing the limits of quantum mechanics. As technology advances, we may discover new phenomena and applications that further expand our understanding of the quantum world. Quantum entanglement is another strange phenomenon related to matter waves. When two particles become entangled, their wave functions are linked so that the state of one instantly affects the state of the other, no matter how far apart they are. This has profound implications for communication and information processing. Quantum teleportation uses the principles of entanglement and matter waves to transmit the state of a particle from one place to another without physically moving the particle itself. While still in its early stages, this technology could one day revolutionize communication and computing. Quantum sensors use the wave properties of matter to make incredibly precise measurements of time, gravity, and other physical quantities. These devices are already being used in navigation, geology, and fundamental physics research, demonstrating the practical power of quantum mechanics. Quantum cryptography uses the principles of quantum mechanics, including matter waves, to create secure communication channels. By exploiting the uncertainty and entanglement of quantum particles, it's possible to detect eavesdropping and ensure the privacy of information. Quantum optics is the study of how light and matter interact at the quantum level. Matter waves play a crucial role in this field, helping scientists develop new types of lasers, sensors, and communication devices that operate on quantum principles. Superconductivity is a phenomenon where certain materials conduct electricity with zero resistance at low temperatures. The wave nature of electrons is key to understanding this effect, as electrons pair up and move in coordinated waves, allowing for lossless current flow. Bose-Einstein condensates are a unique state of matter formed at extremely low temperatures. In this state, atoms behave as a single quantum wave, demonstrating the collective nature of matter waves on a macroscopic scale. This discovery has opened new avenues for research in quantum physics. Quantum simulation uses controlled quantum systems to model complex phenomena that are difficult to study directly. Matter waves are essential for these simulations, allowing scientists to explore new materials, chemical reactions, and even the behavior of the early universe. Quantum metrology is the science of making measurements with quantum precision. Matter waves enable the development of ultra-precise clocks, sensors, and measurement devices, pushing the limits of what's possible in science and technology. Discovery of matter waves and the de Broglie relation has transformed our understanding of the universe. From the tiniest particles to the largest structures, the wave nature of matter is a fundamental aspect of reality. As we continue to explore the quantum world, the legacy of de Broglie's insight will inspire new discoveries and technologies for generations to come.